and Doris Day, Red China, Johnny Ray, South Pacific, Walter Winchell, Joe DiMaggio, Joe McCarthy, Richard Nixon, Studebaker, television.
So this one has part A and B. So part A says, it gives us, let's see, what do we have? C of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. Okay, so this can be characterized by, this actually looks familiar. It's like the sine, sine x one, right? How we have, no, cosine, sorry. This is the cosine one because it's like an even, the even terms survive. So this can be represented by the infinite series as -1, and this gives you the alternating signs part, right? And then we have x to the 2n over 2n factorial. So anything times 2 is going to be even, right? So that gives you your even numbers. And anyways, so now we're supposed to find the interval of convergence, or the radius of convergence, I believe. Yeah, the radius of convergence. So let's implement the ratio test, and we'll do limit as n goes to infinity of, and we'll put n plus 1s everywhere. So we have -1 to the n plus 1, and then we have an x to the 2 times n plus 1 over 2 to the n times n plus 1 factorial. Okay, and this is over the normal a sub n. So here I'm just going to skip the part where I like write on the bottom, and I'll flip it up already to the top. So then we have a 2n factorial over -1 to the n times x to the 2n. Alright, so now I'll just simplify here. So we have limit as n goes to infinity of, and I'm going to split up some stuff. So these -1 factors, they just go away because they're just going to come out as positive ones anyways. And then if we distribute the 2, we get x to the 2n plus 2, right? So x to the 2n plus 2 is actually this, okay? And then over 2n plus 2 factorial times 2n factorial on top, and then the x to the 2n. Okay, so I guess I'll just cancel these out for now, because that's what comes out. And then we also have to deal with these factorial things. So we're going to end up with something like this. So then we have our x squared on top, and then this is going to be 2n plus 2. We can break this down a little bit, times 2n plus 1, and then 2n factorial. Okay, and that's times a 2n. Ooh, that's a factorial at the end there. Sorry, I'm changing the screen. Okay, 2n factorials at the end. You get the idea. So then those cancel. Okay, so this is what we're left with. And again, like I've done before, this x squared, that doesn't really matter in the limit. So we're going to bring that out to the front to be a constant. Okay, so we have rho equals limit. Well, I'll write, like I said, I'll write that in front as n goes to infinity of 1 over, and what's left inside? We have a 2n plus 2 on the bottom times a 2n plus 1 on the bottom, and everything else canceled out. So now we can just plug in n, and once we do that, we're going to get 0, right? Because this is all like 1 over infinity stuff. So then we just get 0, which, so we get that rho equals 0, which is always less than 1. So this is pretty important. This is that one case where this is always true. So r equals infinity. Our radius of convergence is infinity. So technically, the interval of convergence would be -infinity to infinity. Okay, so that's just a bonus there. Okay, now for part B. So part B, this is dealing with the differential equations, or the diffie-q's. So this one, the initial conditions they give us are y double prime equals -y, and y of 0 equals 1, and y prime of 0 equals 0. And it tells us to prove that okay, I'll just write it out. Prove that c of x and f of x equals cosine x are both solutions. Okay? Alright, so first of all, I'll just write out c of x so we know what we're working with. So we have our 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus etc. And then this is equal to, as we said before, this is like the cosine function, right? So we have n equals 0 to infinity, and here's the alternating part here. And then we have x to the 2n over 2n factorial, okay? So what we're going to do is prove that the second derivative of this function here is equal to the negative of the original function. So let's find the negative of the original function. So we have negative c of x equals 1, well, this is negative 1. Well, we don't need to write out that. I'll actually just, these terms, you can write them out if you want to illustrate better like what's actually going on with the terms themselves, but I'm just going to deal with this side here, okay? So if we just insert a negative, negative 1 times all of this, I'll show you how that factors in to what we're going to be writing. 2 to the n over 2n factorial. So this negative 1 out here, that could just combine in here, right, with this negative 1 to the n. And technically, negative 1 is negative 1 to the 1 power, right? So we could just add it in there. So here's where we get negative 1 times n plus 1, okay? Because you could break this down into negative 1 to the n times another negative 1, right? And that's what we had out here. Now we're just combining it in the exponents. So, yeah, so this is what we have at the end. So this is our negative c of x. This is like our negative y. Now our job is to find c double prime of x and then compare it, and we'll see. So let's find c prime of x first. So then we get, and again, I'll just work with this part because you can do the terms if you want, but it'll just be equal to whatever's in the series. So that would be, we're going to rewrite this part, and what we're going to do now is we have a 2, this power on top is going to come down in front. So we're going to have a 2n, okay? And then the negative 1 to the n is just going to stay there. And then we have x to the 2n minus 1 on top. And then down here, that's 2n factorial, but I'm just going to rewrite it for more convenient uses. So then that can be represented by that, right? So then these 2 n's in front cancel, which is nice. And then basically we end up with something looking like this. So then we have our negative 1 factor in the front there. And then we also have x to the 2n minus 1 over 2n minus 1 factorial. Okay? And now we're just going to do this one more time to find c double prime of x. So I'll start it down here, and I'll probably have to continue on the next slide. So now we have, let's see, now we'll have something like n equals, oh, really quickly, going back, sorry, here, what we just calculated for c prime of x, the n actually has to start at 1 now, because on the bottom here you see that if n were to be 0, we would have negative 1 factorial, which I believe is mathematically impossible or something. You're only supposed to have positive numbers that go down to 1, like 3 times 2 times 1 is 3 factorial, so I think that wouldn't be possible if n were 0. So something like that. But basically, we have an n minus 1, or n equals 1 down here. So that's going to carry on to the second derivative. We're going to have n equals 1 to infinity, and then we're just going to do the same thing as we did on the last one. We'll bring the power down in front, so then we have 2n minus 1 times this negative 1 factor there to the n, x to the 2n minus 2 now, because we're subtracting another one from the power. And then this factorial down here breaks down into 2n minus 1 times 2n minus 2 factorial, and these in front cancel again, and we get that this is going to be equal to this, n equals 1, n starts at 1, and then we're left with the following. 2, well, I guess you could write, yeah, 2 to the n, I'll just break it up just for the sake of breaking things up. Okay, so it looks like that, right? Okay, so now we're just going to take this and compare it to, we're going to take this final answer here, and compare it to this one. Alright? So if you see, if you were to compare these, they do look different, but here's where the negative n starting at 1 for the second derivative comes into play. So let's say you plug in a 1 here, then essentially what you would get is the same thing as if you were to plug in a 0 here. Okay, so if you were to plug in a 1, you would get negative 1 to the 1, so that's negative, and then for the x part, we have x raised to the 0 power, so we would get negative 1, and then down here you get 0 factorial, so that would be negative 1. That would be our first term. So a1 would equal negative 1, and then what we would get over here is that if you plug in a 0, then you get negative 1 to the 1, and then x to the 0 is just 1, and 0 factorial is just 1, so that would also be negative 1. And if you were to continue that for like n equals 2 down here, and n equals 1 up here, then you keep getting the same answer. So basically we have confirmed that for c of x, c double prime of x equals the negative of the original function. Okay, so that's kind of like the first part of kind of a whole lot of parts that we have to prove. But yeah, so yeah. All right, now we'll prove the f of x one. So this part here, that one is much simpler. I will tell you that. So we'll start that on the next slide. So we have f of x equals cosine x, and we're supposed to prove that f, the negative of this function, is equal to the second derivative of the function. So let's do that. We'll take the first derivative, which is negative sine x, and then our second derivative is naturally negative cosine x, which is obviously the negative of f of x. So negative f of x equals negative cosine x, which is equal to then the second derivative. So that one was proved pretty easily. And the last part here, it said that we have to make sure that the initial conditions remain true. So basically that y of 0, I believe, is 1. And they also gave us that y prime of 0 equals 0. So basically, I'll go back to the c ones. So we have that when c is 0, our expanded form looked like this, right? Something like that. These are the even ones, remember? And then etc. blah blah blah. And when you plug in 0 for x, all of the terms after 1 basically just become 0. So our answer is 1. So that's good. So that fits the first condition here. And let's check f of 0. Then we have cosine 0, which equals positive 1. So that's good as well. And then the last part here is checking this one. So we have c prime of 0. And the terms there would look like negative x, because you just take the derivative of all the terms. Negative x plus, x to the third over 3 factorial minus x to the fifth over 5 factorial, etc. So when you plug in a 0 for the x's, all the terms just become 0. So it's 0, which is good. That matches. And the final one is checking f prime of 0, which equals negative sine 0, which is also 0. And that's it.